We have a new topic, new section today. That's the Cauchy-Euler equations. So far, we've been able to find solutions to higher order differential equations with linear differential equations with constant coefficients. And then we took care of the homogeneous portion, then we did the non-homogeneous portion. And so now we're going to start looking and moving away from constant coefficients a little bit. And we'll take a look at a special case where your differential equation follows a specific pattern. And so a linear differential equation that looks like this, where you have x to the n paired up with y to the nth derivative, or the nth derivative of y is paired up as a term. And then the idea goes all the way through here. So if you have a scenario like that, a linear differential equation that looks like this, and this is called a Cauchy-Euler equation. So just like before with any higher order differential equation, we're going to solve for this by first looking for the homogeneous portion. And then we'll find a particular solution and pair them up. So if you remember, we often referred to the homogeneous portion as y sub c, and in a particular solution is y sub p. And so your solution will be y sub c plus y sub p. And then we solve assuming, so here's our trick. In the past, we've been solving for these things where we assume that the solution is e to the mx or something like that. This time, for this particular case, we're going to assume that your solution looks like x to some power. So it's a power function. And then we have to decide what m is, or along the way, we'll end up finding what m is equal to. Just like before, this is going to come up with a characteristic equation. And so here we're going to take a look at the example where n is equal to 2. So what does a Cauchy equation, Cauchy-Euler equation look like when n is equal to 2?
Would be like the coefficient times squared times the second derivative of the function, and then first derivative times x times constant.
Okay.
And then just constant and y. I mean, yeah. Equals,
whatever it is. So this is an example of a Cauchy-Euler equation, a non-homogeneous Cauchy-Euler equation of order 2. So let's take a look at this and try to see what the corresponding auxiliary equation is going to look like. Now, in the past, we had am squared or a2m squared plus a1m plus a sub 0. So we have to be careful that in this case, we're probably not going to get that. Okay, we won't get that. So let's see what we actually do get. So we're going to let y equals x to the m, and then we're going to need the first and second derivatives for this. So we'll take the first derivative and the second derivative. No, not quite.
I mean, you have the higher one.
Only if we end it times 3 times 2 times 1.
Oh, okay. Yeah, yeah.
But there's no guarantee that that's going to happen.
Oh, yeah. Never mind. Sorry.
All right, so we put that into here and see what we get. We're going to get a sub 2 x squared, and then we'll put what we found for y double prime, m minus 1 x to the m minus 2. And then we have, oh, I need more room. Can I move this?
Oh yeah, see that thing? That little circle you popped up. Once you see that, you drag it around. Yeah, and when you let go, you want to get it right once.
I will. I don't know.
Yeah.
I was a little afraid about starting with a new computer in the middle of the semester. Here we go. We're working it out. A sub 1 x, and then the y prime that we found was m x to the m minus 1, and then a sub 0 x to the m. And then we're going to take a look at, because what we're going to need to do is we're going to need to find the homogeneous part. So we're going to first take a look at the homogeneous portion of this to find our y sub c. All right, where are we at? We got a2 x to the m, because that's x to the m minus 2 plus x squared. And then we got m minus 1 plus a1 x to the m again times m plus just a sub 0 x to the m. So if we factor out an x to the m, we have our characteristic polynomial m minus 1 a sub 2 plus m a sub 1 plus a sub 0. And remember that we're assuming that our solution is of the form x to the m, so we're interested in solving for m. Okay. So if we multiply this out, this is m squared minus m with some constants. I mean, you can write this as a quadratic, which is what it is really. Let's see if we can write it as a quadratic. It would be a sub 2 m squared, and then I have 2 m's plus a sub 1 minus a sub 2 times m plus a sub 0 is equal to 0. So this is our equation where we're solving for m, and m is a second order polynomial, so we can use a quadratic formula or whatever. Okay. All right. So if you do have a second order polynomial, a second degree polynomial, I should keep using the word degree for polynomials and order for differential equations. Second degree polynomial, and you're solving for m, you're going to have two solutions. So either the solutions are two distinct real numbers, one real number that's repeated, or you actually have complex numbers. And so in those scenarios, should I just give you the answers? All right.
And,
Yes. So the results. I should just have this in. Yeah.
Can we have the original, like, one whole file uploaded so that we can copy and paste?
I don't have it all ready. I mean, I just have Word files right now. I can just copy and paste OneNote files and stuff, but I don't have a way of organizing this yet. It's just the first time using it. So here are the possibilities. If you have two distinct real numbers, m1 and m2, then those are just the powers of the power function. And assuming they're different, distinct, then x to the m1 and x to the m2 would be linearly independent, so we can just tack them up. If we have one repeated real root, then our x to the m is our answer, is our root. But I won't have another linearly independent function. And so, you know how in the past we simply multiplied by x? Well, in this case, it's a little bit different. If you have a repeated root, you multiply by an ln x. And we don't have to go through the work. I don't know if the book does it. Maybe they do. But you can look up, or you can go through the process yourself in the reduction of order if we have one solution already. So that's section 4.2. If we have one solution already, there's a process of finding our second solution by the reduction of order, by some sort of substitution, and then you can get that our second solution. And I just want to highlight, maybe I can highlight. I just want to highlight the fact that our second solution will have an ln x instead of just a regular x. And then lastly, if we have complex conjugates, then our solution will almost look like our complex conjugate, except this time it has that ln x again. That's because the complex numbers transfer easily if you have an e to some power, but remember that our solutions are of the form x to the m. So we have to write our x to the m as e to some power to be able to use the sines and cosines. Was that Euler's formula?
Yeah.
Yeah. Well, you don't, not one term, but like the two terms that we're looking at. I think in general, we just leave it as one term. All right. So I guess the et cetera means I should finish this. So our solution becomes, these should all be y sub c's. Oh, it's already up here. Never mind. Yeah, so y sub c is going to be c1 x to the alpha cosine beta and all that stuff.
Wait,
factor out the next thing out.
Yeah, you could.
Is, so it's just ln x times bi or ln x to the bi power?
ln x.
Is it raised or is it on the same line?
This is raised up here,
Oh, okay. Okay.
and then it goes down as a coefficient.
Okay. Oh, I see. In the front.
Coefficient of the ln x. Right? Hmm? That would just be 1 if you graph e to the ln x. That would be only 1 on the positive side. Because ln doesn't have zeros or negative numbers. All right, let's do an example. We got a whole bunch of examples here. Which one should we do? 10-sided dice. Pick a number between 1 and 10. Let's do number 8. I don't know. All right, let's do number 8. So I think I can grab a picture. This one or that one? Why does that have to be right click?
Are we going to do like higher than?
Put it on a clipboard and then.
Wow, that's yeah. I have to streamline that. All right, let's do an example. Let's see. Even the snipping tool isn't so handy, but anyways, that's what I used yesterday. All right, let's do an example. We got x squared y double prime plus 3x y prime plus 4y is equal to 0. So it is, in fact, the Cauchy-Euler equation. It's a homogeneous equation, so we only have to worry about finding our homogeneous portion. And it's second order, so it should follow. This will give us practice on finding the auxiliary equation. So you could eventually memorize a formula that comes with this, but if you just remember the basics, our solution is going to be x to the m, and then we got the first and second derivatives. Okay, so this stuff is always going to be the same for second orders, and then if you got higher orders, then you'll deal with it. So you put that in here, we're going to get x squared times m minus 1, x to the m minus 2. And it's pretty much guaranteed that you're going to come up with an x to the m for each term that you're going to be able to factor out. So that's one thing to look out for and think about streamlining your process. Oh, we have a 3x, and then the y prime is going to be m x to the m minus 1, and then minus 4y, which is x to the m. So again, you got x to the m as a factor common to all these terms. So we could take that out and pretty much ignore it, divide it out or whatever. And then we have, what do we have left? We have m squared minus m plus 3m minus 4. And this is your auxiliary equation. So m squared minus plus, yeah.
Are we gonna do these with like higher order than?
Oh yeah, so this is just the case for n is equal to 2. It's just a special case because we can do it quickly. But yeah, this could go third, fourth order or whatever. Yeah. So you're gonna solve, higher order polynomials and yeah, just like the other one. Speaking of factoring, nope. So quadratic formula, negative b plus or minus the square root of b squared minus 4ac. So it'll be positive 2a. So this would be negative 2 plus or minus the square root of, this is 1620. I think I can factor out a 4, make it look a little bit nicer. So 4 under the square root, that's root 5, and then 2 outside, so that would be minus 1 plus or minus root 5. It's almost the golden ratio. What? You had to complete the square? Do we get the same answer?
Yeah.
Oh, well, good job. Well, this is a real number. All right, these are two real numbers. We got negative 1 minus root 5, negative 1 plus root 5. And so they just fall under this first case category. So your y, your general solution, well, let's write it out first. So you got y1 is equal to x to the minus 1 minus root 5 x. No, not x. No. And then the other one is x to the negative 1 plus root 5 power. So those are just numbers, and so this is just going to be a power function. And then that's your solution. So your constants, and then I guess in any order you want this to be. Okay. Any questions? Seems pretty straightforward. Maybe. All right, let's try to do one that involves the non-homogeneous. See. Is there one we can pick? Now they all seem to have second power here. Oh, just regular. There's one with a third power over here. A couple of them. Yeah, you guys can figure that one out.
You don't like the icon? Well, it would be right with the icon. Is that
Windows Shift S. Is this which one is this?
Yeah, but if it's up to remember, it'll always do that. I want this one.
Oh, good. That's what I want.
I use this tool.
I do too, but oh, why did I choose that one? I don't know. I don't know. What number was that? Oh, okay. Let's do this. Let's so remember that the first part is finding y sub c, and then after you do that, we need to use, because we could actually use, no, we can't use the undetermined coefficients technique. I was looking at the right-hand side. It looks like we can initially, but the left-hand side doesn't have constant coefficients, so we have to use variation of parameters. So variation of parameters is the one that involves the Wronskian. Remember that? That's where we're going. So let's figure out the y sub c first. Yeah. But taking the derivative of this is a product rule, so that's what I was. Anyways, we got y is equal to x to the m. Y prime is equal to m x to the m minus 1. Y double prime is equal to m minus 1 x to the m minus 2. So we have x squared times m minus 1 x to the m minus 2. And then we have a minus 2x times, oops, I keep putting big parentheses around that. All right, minus 2 times x times m x to the m minus 1 plus 2y, and y is equal to x to the m. And that's equal to 0. I should use a darker pen. What? Feel like a rookie. So we factor out an x to the m, and then we have m minus 1 minus 2m plus 2. So we got m squared minus m minus 2m, that's minus 3m, plus 2 is equal to 0. So 2 times 1? So it was m minus 2, m minus 1, and then you solve for it, become positive. Does that look good? So it looks like we're supposed to have our y sub c to equal to c times c1 times x to the first power plus c2 times x to the second power. Let's put a box around that so we don't lose it. Now, variation of parameters. Remember the u's and the w's, Wronskians. So we need u prime is equal to W over W. So UI is, there's only two of them. So U1 prime is going to equal to W1 over W, and then U2 prime is going to equal to W2 over W. This should be capital W. I don't know, it makes a difference. And so we need to find all these Wronskians. So let's find out the original Wronskian based on our fundamental set. We have our first and our second functions to be x and x2. I'll call that y1 and y2. The derivatives going down, the derivative of 1 is, the derivative of x is 1. 2x. So we have 2x squared minus x squared. That's just x squared. So that's my denominator for my u primes. Now I need to find a W1 and W2. So remember, the W1 replaces the first column with the right-hand side and 0. Is that right? Is that how it goes? So this is our fx. Is that right? Variation of parameters? Oh, that's what it was. Thanks. 0 first, and then fx. And so we'll do the same over here. All right. We're finding determinants. So this is going to be 0 minus x to the 6th e to the x. And over here, it's x to the 5th e to the x minus 0. Okay. Whoa, too far. All right. So our u prime 1 or u1 prime is going to be w1 over w, which is minus x to the 6th e to the x divided by x squared, which is negative x to the 4th e to the x. Looks like a long-winded integration by parts. And then the other one, u2 prime, is w2 over w, which is x to the 5th e to the x divided by x squared, which is x to the 3rd e to the x. Another integration by parts. So, do you know how to do integration by parts? So there's this UDV business. Is it UDV? UV, something like that? I don't know. There's this trick that I saw some high school students do. They have to do integration by parts multiple times. They list x to the 4th on one side, and then they have e to the x on the other side where you're supposed to be integrating. And then here they just keep taking derivatives. And in here they just take antiderivatives. And then, how's it go? I think it goes like this. This thing minus this thing plus this thing minus this thing. Oh, I need one more. Something like that. That's pretty much how that works, isn't it? So with a negative in front, with a negative in front, our u sub 1, this is, darker one. We're going to get x to the fourth e to the x minus 4x cubed e to the x plus 12x squared e to the x minus 24x e to the x plus 24 e to the x. And then distribute the negative sign because it was negative to begin with. Okay. And so U2 will be similar. What is it? It's going to be x cubed e to the x minus 3x squared e to the x plus 6x e to the x plus 6 e to the x. I mean, you can factor out an e to the x and stuff, but leave it all there. Okay. So I think we have our particular solution. I can write out the particular solution, but I think it'll be more work than needed. So let's just put it all together at the end. So this is the whole solution with the homogeneous portion. So it's going to be C1 x plus C2 x squared. Oh, I guess we should have done it because maybe we could have simplified it. I don't know if it's going to cancel, but we can definitely simplify it. Sorry, I'm going to step back a little bit. Boy, I can't get this thing without the mouse for some reason. So I'm going to step back and find y sub p first. And remember that y sub p is u sub 1 times y sub 1 plus u sub 2 y sub 2. So you have to incorporate the y's that we found. So y sub 1, according to what we have here, is x. And y sub 2 is x squared. So u sub 1 is this big whole thing times x. So I'm going to multiply everything times x, and I'm going to distribute the negative sign. And you know what? I'm going to factor out an e to the x as well. So minus x to the fourth plus 4x cubed minus 12x squared plus 24x plus minus 24. And then the e to the x gets factored out. And then the next one, we're going to multiply this by x squared. And then I'll also factor out an e to the x. So that's x cubed minus 3x squared. I'm not changing the signs. Plus 6x plus 6 minus 6. Oh, here, yeah. They're alternating. I didn't factor out the first x. That came from y1. In fact, maybe I should relabel that. So what do we have? We have change colors. E to the x can factor out of this whole thing. And then we're going to have matching powers, I think. I got x to the 5th. We got negative x to the 5th, positive x to the 5th. Pardon me? Factor out the x. Oh, yeah, I was going to distribute it and see if I can work it out. Because I think we can simplify this into one big polynomial. So I have, let me write it all out. So negative x to the 5th plus 4x to the 4th minus 12x to the 3rd plus 24x squared minus 24x plus x to the 5th minus 3x to the 4th plus 6x to the 3rd minus 6x squared. And let's see stuff disappear here. That disappears. This is going to be x to the 4th minus 6x to the 3rd minus 18x squared, and then 24x by itself. All right, so that's what we'll use. So we had an opportunity to simplify our y particular. And then here's what we got, x to the 4th. So that's done. Minus 6x to the 3rd, that's done. Minus 18x squared. And then the last one is plus 18. Minus 24x squared. Nope, x. No, it's a lot to keep track of. All right. So with this little bit of work, you could try to make your y particular a little bit simpler. Yeah. Because this one had a negative in front of it, and this one didn't. I think that's, yeah. Okay. Did you guys ever have to do this for Calc 2? Professors don't usually go more than twice. Yeah, see, when I was going through college, I didn't see that either. It's a high school thing. They want you to do well in the on the AB test or whatever the calculus thing is. Yeah, it does work. But usually teachers don't want to go. I mean, once you know the simple process or the idea behind doing integration by parts multiple times, they're not going to ask you to do it 5 times. No. All right, that's good. What else do we have to do here? Number 34. Oh, yeah. Yeah, so
like we're not supposed to know to do that. It would be in the question.
I think so. What they're trying to do here in this particular substitution is they're saying that if you have a Cauchy-Euler equation, you can actually transform this equation and make it look like an equation that we've dealt with, which is an equation with constant, you know, it's a linear equation with constant coefficients. So ideally, because of the nice pattern that this has, we should be able to, you know, somehow transform this, make it look like those problems that we've been dealing with in the previous section. So by doing this, they say there's a particular substitution that you can take, so you can transform the equation into a differential equation with constant coefficients, and maybe that would be easier to solve. Not that it would be easier to solve, because it seems like it would take more steps, but it's an interesting process. So let's take a look at it. It's a little tricky though, because the substitution involves, whenever you do a substitution, it involves changing the variables. Just like a simple u substitution in integral, you change a dx to a du or whatever it is you changed into. And so we have to keep track or keep in mind that we're going to do that change. Let's do, should we just be brave and do number 36? All right, see if I can remember. Window Shift S? Yes, I like it. Anyways, these things don't have answers, so it doesn't matter if it's right or wrong. I'm just kidding. It's going to be right. I don't know. Special substitution. So I'm going to put the problem down here, but I'll write some comments. So the idea is to do a substitution. Our substitution is going to be, what was it again? E to the t. And so remember that our y prime is actually dy dx. And so somehow with this transformation, with a substitution, we want to transform our dy dx's. Instead of dy dx's, we want dy dt's, because we're going to change our variables from x to a t. So what we're going to assume is that t is a function of x. So we're going to want t ln. Wait, let me get this straight. So y is a function of t. Well, we still want to solve for y. And we're switching variables from x to t. dy dx times dx dt to get dy dt. Is that what you said? Sure, yes. Why not? Well, no, I think what we want is yeah, but I think what we want is dy dx by itself. Well, dy dx, right? But then we're going to want our equation to be dy dt, right? Oh, yeah, we're not going to do it that way. The point in this is to make this substitution. By making this substitution, we're going to go back to the constant coefficient business and make it not a Cauchy Euler equation anymore, but be able to solve for it the old way. It is. That's why we're doing it that way. That's why we're doing it this way, to see the transformation back. Right. Yeah, hopefully. We could. I don't know. Well, let's try it this way. So this chain rule isn't exactly what I was looking for, because I wanted to replace the dy dx's with dy dt's. And so I think what we want is we want y originally is a function of x. We want y to be a function of t, which is a function of x, and that's the composition that we want. And so we can say that dy dx is actually equal to dy dt times dt dx. So if that's the case, then this is a substitution that we mentioned, but this is actually what we're going to try to shoot for, is to find derivatives. We want the dt dx, you want t as a function of x. And because t equals ln x, dt dx is going to be 1 over x. So dy dx is going to be 1 over x times dy dt. Man, it's a lot of work. All right, let's see where we're going with this. We have dy dx. We have our substitution for y. Y is here, just going to remain y. We need y double prime. So we need the derivative of this thing with respect to x, dy dx, and that is the derivative of this thing with respect to x. Oh man. So it's the derivative of the first times the second plus the first times the derivative of the second. What is that? dt. So y so dy dt is a function of t, which is a function of x. So we're going to need the chain rule. So this is going to be the derivative of dy dt with respect to t times the derivative of t with respect to x. Maybe we should have done a second order. What's dt dx? For those of you who are still following, 1 over x. All right, so I think we got the second derivative, y double prime. We have this and this. Well, there's a 1 over x and a 1 over x. Well, let me write it out first. Negative 1 over x squared dy dt plus 1 over x squared, because I have these two. And then I have e squared y dt. Yeah, that's it, right? All right. Now we did pick a third order, so we need to take the derivative again. Or we could just go back and select another one, the second order. I want to go back and select another one. Let's pick a second order one. It's all being brave and stuff. Yeah. Well, let's finish this. I don't know, 1, 2, 3, 4, 5. Which one? Let's do a homogeneous one. Shall we? All right, so we have to remember in our notes we're going to change problems here. All right, we're going to focus on this one based on what we have. And what do we have? We have our y prime and our y double prime. So let's do the replacement. We have x squared and we have y double prime, which is, oh, let's factor out a 1 over x squared here. 1 over x squared factored out. And then I'm going to switch to order so that the positive one's first. D squared y dt minus dy dt. So that 1 over x and the x squared conveniently will cancel. And then you got 9x, and then the y, where are we? Here, this is our y prime is 1 over x times dy dt. Again, the x's will conveniently cancel. So we can simplify this a little bit. D squared y dt minus dy dt minus 9, cancel out the x. Dy dt plus 25y is equal to 0. Dy dt, d squared y dt squared minus 10 dy dt plus 25y is equal to 0. So this is easier to do the auxiliary equation because it's literally just the coefficients, right? So our m squared minus 10m plus 25 is equal to 0. M is equal to 5 twice. And so we got y of t. Now I'm being careful here because this is a function of t. Y of t is equal to y1 of t is equal to, what is it, e to the 5t. And y2 of t is equal to, because it's repeating, what happens? It's x e to the 5t, right? Now, unfortunately, this isn't our answer because we changed variables, right? So now we want to change back. So there's a couple ways to do the change back. We can use x is equal to, or y is equal to, or t is equal to, sorry. So we have t, where is it? T is equal to ln x. So y1 of x is equal to e to the 5 times ln x. Y2 of x is equal to x. Wait, there's an x in there? This should be a t. Yeah, sorry. So this is ln x e to the 5 times ln x. All right, if you can somehow remember your ln properties, this would be x to the 5th. And y2 is going to be x to the 5th ln x. That's a good question, and the answer is I don't know. I think the Cauchy-Euler equation is set up so that it would work either way. I don't think so. Which is simpler? So no, I don't think I'll force you to do one way or the other in something like this. But yeah, except they kind of did it backwards. So if we would have done this using the Cauchy-Euler equation way of doing things, then we should have gotten the same results. Which we can write up, by the way. Let's just write it up. So your final solution is going to be y is equal to c1 x to the fifth plus c2 x to the fifth ln x. Okay. Yeah, I don't think I'll force you to do it one way or the other. This is actually, this seemed easier once it was all constant coefficients. The hard part is remembering these substitutions with remembering these substitutions here to replace that. So, you know, in fact, the substitution that you would make here, it's almost like equivalent to the characteristic equation. But in any case, you know, you just do one, whatever way seems easier. Okay, I think there's another substitution that we can examine. I don't know if we will. Another substitution where we let t equal negative x. The other thing I was interested in is the changing, instead of having an x, it would be x minus 1 or x minus 3 or some other weird thing like that. But anyways, you guys can read through that. Hopefully there aren't that many homework problems similar to this. Well, let's see. Is there? No. What is the temp? 4. What did we just do? 4.7 or 4.8? What was 4? Oh, 4.5 is the annihilator. Green's function is 4.8. What? 4.7. Thought I had flash. It's just hidden. Oh, we didn't do an initial value problem, but here's one. Good luck. All right, see you guys on Thursday.